Hello guys and welcome to Engineering Key Tutorials. So in this video we're talking about flexural behavior of rectangular concrete beam at every stage and every element that has reach. Imagine we have a simply supported rectangular beam and we load it in the lab from starting apply the load to the fail. It will reach 3 stages as this journey. So the first limit or the first stage, it's called before cracking stage. So you can see in this limit we will calculate MCR, which is MCR is M cracked. So to not be confused, this bending moment just before beam start cracking immediately. In this stage all the cross section is resist. To can calculate the neutral axis and the stress distribution, at the first we have to calculate the position of the neutral axis. But we have a problem, we have two materials, the steel and the concrete. In this case we have to convert the cross section to equivalent cross section as any composite section. So we will change the area of steel by n-1 times AS, which is N is the modular ratio. It's equals to ES divided by EC, which is ES is the modulus of elasticity of steel and EC is the modulus of elasticity of concrete. It's almost equals 8. So what is specifically the N, or what is specifically the modular ratio? According to Hooke's law, the plane section before deflect remain plane after deflect. So we are still in the linear elastic region in this strain distribution. So also the steel and the concrete bonded together strongly, so the steel and the concrete will be strained with same amount. Hence the steel and the concrete strained with same amount, so the epsilon s equals epsilon c. Epsilon s equals sigma s divided by es, and epsilon c equals sigma c divided by ec. So sigma s equals to es divided by ec times sigma c. So the stress in the steel will be N times or ES divided by EC times sigma c, which is N is the modular ratio, or it's physically how much steel stressed times the concrete stress. But here we substitute with n-1 because we used all the area of cross section. So to calculate the area moment of inertia of this transformed cross section, at the first we have to calculate y bar. It's equals to bh times h divided by 2 plus n-1 nas times d divided by summation of area ph plus n-1 times AS. So we get the y bar. Then we using parallel axis theorem, we have to calculate area moment of inertia of uncracked transformed section. It's equals to bh cubed divided by 12 plus bh times h divided by 2 minus y bar square plus n-1 times a times d minus y bar square. In this case we neglect the area moment of inertia of the bars about the centroid of the bar because it's very small. Okay guys, then guys we have to calculate the MCR as stress equals my divided by I. So FR equals MCR times YT divided by I uncracked, which is FR is rupture modulus of concrete and YT it's the distance from the neutral axis to the extreme tension side or extreme fiber as the tension side, and I uncracked, which is what we calculated. MCR equals I uncracked times FR divided by YT. The rupture modulus of concrete, it's equals to 7.5 square root of FC prime. In this case we substitute with FC prime with PSI. Yeah. So let's move to stage 2, the after cracking section, or in the serviceability limit state, or also it's called elastic limit state. At this limit, as you can see, the cross section cracked from tension side and rebars takes all the tensile stress, but stress remain also linear elastic. In this limit we wanna calculate the M elastic. So the step 1 to find location of neutral axis using also transformed area method, as you can see. So step 1 to find location of neutral axis also using transform area method. As you can see, this part above neutral axis height is called KD, which is K is a fraction of D, which is D also is the effective depth of the cross section. Its distance from the top fiber of the cross section to the center of the rebar. Also, the strain distribution is linear. To find the K value, so we use the method of summation moment of area above neutral axis equals summation moment of area below the neutral axis. So BK times D times KD divided by 2 equals to NAS, which is here we use N only because the concrete around the pre-bars is neglectable. Okay, times D minus KD. So we simplify the equation. It's equals to NAS D times 1 minus K. So PD K squared divided by 2 equals to NAS minus NASK. So K squared divided by 2 equals to N rho minus N rho K, which is rho the steel ratio to the effective area of cross section, which is the effective area is the P times D. So after solving this quadratic equation, K equals to square root of N square rho square plus 2 N rho minus N rho, which is K depend on amount of steel. Then you have to calculate I cracked. It's equals to P times KD cube divided by 3 because we take the moment of the moment of inertia about the edge axis, not centroidal axis, plus NAS times D minus KD square. So this I cracked used in serviceability equations such as deflection, or also we calculate the I effective that we will talk about in the next videos. It's something between I cracked and I gross of the cross section. We use it in the deflection calculations. So to find M elastic, we have to use the equation M equals T times D minus KD divided by 3, which is the distance from tension force to the compression force. So we will substitute T by ASFY times 0.4 because we have two limits of elastic cross section in ACI. We can use 0.4 F yield or 0.5 FC prime. We substitute by these two values and the smallest value will be controlled. So the M elastic equals to AS times F yield times 0.4 times J times D, or 0.25 KD FC prime P times J times D, which is J is 1 minus K divided by 3. So guys, let's move to the stage 3. It's called ultimate or called the design stage. So guys, at this limit we have to calculate M nominal, which is the bending moment that cross section reach at the failure. So in this limit, as you can see, the stress distribution is not linear, but we assume the strain distribution is linear. Also, as you can see, the stress strain curve of the concrete have the same shape of the stress distribution of the cross section. At the top fiber we have 0.85 FC prime, and below it we have a FC prime, and the last part is linear. As you can see, the same shape of the stress strain curve. Also, the stress strain curve of the steel at the ultimate we have stress F yield, which is corresponding to epsilon yield equals 0.002. So guys, to calculate the compression force we have to find the area of the stress, but this shape need integration to find the area. So we simplified it to concrete equivalent block with depth A, which is A equals to beta 1C. Also beta 1s depend on FC prime value. You can find it in the ACI. Also, if you look at the stress strain curve, it's utilized horizontal after F yield because in the design we assume F yield is the failure stress. Once steel reach F yield, considered fail. So strain corresponding to F yield equals to 0.002. According to ACI 318, F strain of steel reached 0.005 with concrete strain reaching 0.003, it's considered a tension control section. Also, ACI consider the minimum strain of steel equals to 0.004, corresponding to strain 0.003 of concrete. So the maximum steel amount give you the minimum strain which is equal to 0.004. At the first, we have to find A value. To find A, we have to apply this equation. T equals C, which is T is the tension force at the rebars, and C is compression at the cross section of concrete block. So AS times F yield equals A times B times 0.85 FC prime. So A equals to AS F yield divided by 0.85 FC prime B. So we get A value. Then we have to calculate MN or M nominal. We can take tension force times the distance between tension and compression, or compression force times distance between compression and tension. In this case, we can take tension force, it's easier. Mn equals T times D minus A divided by 2, which is also we calculated A value, so we get M nominal. But in this case, we can use M nominal in design. We can use something called M ultimate, which is M ultimate will be equals or less than phi M nominal, which is phi is factor depends on the steel strain value at the failure mode. So phi equals 0.9 if epsilon T or epsilon at rebars higher or equals 0.005, which is the tension control section. Also phi equals 0.48 plus 83 epsilon T or epsilon S, which is the strain at the rebars, if epsilon T bigger than 0.002 and less than 0.005, which is 0.002 is the compression control section and 0.005 is tension control section. So to calculate epsilon T or epsilon S co-distribution similarity triangles, it equals to 0.003 times D minus C divided by C. Okay guys, so finally we wanna talking about the three types of the cross sections. So we have over-reinforced section. We have over-reinforced section, as you can see, at the strain of concrete or the maximum strain as the concrete reaching 0.003, the epsilon steel or epsilon as the tension side will be less than epsilon yield, which is 0.002. So in this case, we have huge amount of rebars. It prevent the cross section to yielding when the concrete reach the failure strain. Type of failure called brittle failure, because the concrete reaching the maximum amount of the strain and steel remain less than epsilon yield. So it's not good cross section. It's bad because it's brittle failure and not give you any sign of failure. So guys, the second type of the cross section is called balanced reinforced section. It means at when the strain at the concrete reaching 0.003, which is failure strain of concrete, the epsilon tension or epsilon at the steel equals to epsilon yield, which is also not good cross section because you have no sign of failure. It's also brittle failure. You have the under reinforced section, which is when section reaching epsilon C equals 0.003, the epsilon at the steel or epsilon at tension side will be higher than epsilon yield of the steel, which is gives you signs of failure and you can repair the building. It's not danger as the type of the brittle failure. So guys, I hope it's helpful and thank you for watching. Goodbye.